So today we're going to dig a little deeper into this paper by Eric Dollard called The Symbolic Representation of Generalized Electric Wave. Okay, so I already kind of gave an introduction to this paper and talked about the first few sections, but today I want to get in deeper to showing how I can connect Eric Dollard's approach to imaginary numbers and complex numbers to the approach that I've adopted to imaginary numbers and complex numbers. Now, I want to make an important point here. I often call this my method or the method that I'm using, and I want to make it clear that that the idea to use two-dimensional numbers for both real numbers and imaginary numbers I got from Robert Distinti. Okay, so Robert Distinti gave me the idea to display complex numbers like this. This is a notation. This is an approach, I guess you can call it. So I call it my approach. But I don't want anyone to think that I invented this approach, that I'm the first one that came up with this approach. I got it from Robert Distinti. I actually found on YouTube, I found a video where they did it this way. And so it's just very rare that people do complex numbers this way. So I'm going to call this my approach because this is the approach that I've chosen. This is the approach that I want to use for complex numbers. That makes sense to me as a computer scientist. We've got zeros and ones. I like that. This is very simple. And so this is my approach. When I say my approach, I don't want you to think I'm taking ownership of it. A lot of people take issue with that. And so modified complex numbers is my approach to complex numbers. And what I'm going to do today is I'm going to decode Eric Dollard's complex numbers using modified complex numbers. So just as a side note, these modified complex numbers are in fact, at least these ones here, are in fact orthogonal matrices. And so orthogonal matrices are matrices that when you transpose the matrix, when you multiply the matrix by the transpose of the matrix, then you get 1. Okay, so you get ones on the diagonal, positive ones. And so these are all orthogonal matrices because when you take the matrix and transpose it, and in a 2x2 matrix, transposing just means switching that and that, switching that and that. Switching here, switching that and that does nothing. It's the complex conjugate of this 2x2 matrix. And so when you flip like about the forward diagonal, you get the transpose. Or you can think of it like the rows become columns and the columns become rows. So transposing and complex conjugate of a 2x2 matrix are exactly the same thing. And so when you multiply a matrix by its transpose or its complex conjugate, then you get 1. And so that is true of these 4 identities. These are the 4 identities of the modified complex numbers. So complex numbers have 4 two-dimensional identities: this one, this one, this one, and this one. So this is the identity of the positive real complex numbers, the positive component of the complex number. This is a complex number right here. The -1 is written like this. So this is the negative identity of the negative real numbers. And then I, the imaginary number I, is in 2 dimensions, is really just +1 and -1. So you don't have to write I anymore using modified complex numbers. You don't have to write down I anymore. The identity that this represents in 2 dimensions has the +1 on the upper right corner and -1 on the lower left corner. This is I. This is I in 2 dimensions. And so -I in 2 dimensions is you do the complex conjugate, you transpose the matrix. The -1 is in the upper right corner, the +1 is in the lower left corner. This is functionally identical to -I. And so this is why I like modified complex numbers, because you no longer have to write I, or as Eric Dollard writes, J. Electrical engineers, they write J instead of I. But if you use modified complex numbers, you never have to write I or J. You just write the identities as 1 and 0, and you don't have to worry about actually what does this mean anymore. What this means is the I is the backward diagonal of a 2x2 matrix, and that's it. So this is why I like this encoding of complex numbers. It's easy to understand, it's easy to remember. Real numbers are forward diagonal and imaginary numbers are backward diagonal, and that's it. So here in section 2.2 of Eric Dollard's paper, you see how he introduces J. And this J is the I, the imaginary unit that I showed you in the previous slide. And he associates J with time, which is actually really interesting because in the Mandelbrot set, I associate iteration with time. And so I connect time to iteration of the complex plane, which involves imaginary numbers. And so it's interesting that he associates imaginary numbers with something that's temporal. And so here he says, since the dimension time is a fundamental dimension in the important electric quantities, volt, amps, and watts, it is of interest to investigate its properties in relation to electric phenomenon and its representation in electrical engineering calculations. And so the variation of an electric quantity U with respect to time is expressed like this in calculus. And so basically he goes on to say that the symbolic language is not very useful to electrical engineers. Electrical engineers want to do calculations, and he's saying that so one such symbolic expression that has found extensive application, it's useful in describing alternating currents, is this function here. And this is the time rate of variation is equal to J, the imaginary number, times the frequency in radians per second. Okay, times the frequency. So here he's bringing in that wonderful frequency term and the imaginary J, the imaginary number, and relating it to the concept of time. So then he goes on to show the J factor, which he writes plus or minus J is equal to plus or minus the square root of 1. And so, that's one way of saying it. And then he has the omega term here, which is 2 pi times the frequency. So I just wrote over here, I wanted to remind you that 2 pi has the units radians per cycle, and frequency, of course, has units cycles per second. And so omega has units of radians per second, as they said on the previous page. Okay, radians per second. So that's his starting point. And then so he says the factor J is known as the imaginary unit. And of course, they use J. I use I because, I don't know, I guess I'm more of a physicist and less of an electrical engineer. I could use I or J, it doesn't matter. I could go either way. So J is the imaginary unit. And so here he says, the exact nature and origin of this symbol is a mystery to most engineers, and the explanation as to how an imaginary number represents real phenomenon is seldom given. The demystification of this symbol, so he uses the word demystification, which I find really interesting, and its extension to such symbolisms to electric phenomena in general is the subject or the object of this paper. I think he means the subject of this paper. So imaginary numbers, are the subject of this paper. What do they mean? And he has his own way. Of representing imaginary numbers, which is, it took me a long time actually to figure out what he was doing, because I wanted to understand it enough so I could map it to to my approach to complex numbers. And so I had to go through this paper about 10 times before, and it's quite a long paper. Okay, it's quite a long paper. Let's see if I can find it here. Okay, it's got many sections. Okay, it's a very, very, very long paper. And so I wanted to make sure that what I was saying is right, that I could replace what he's saying in his paper with my approach to complex numbers. And so that's what I'm going to hopefully explain over the rest of this video. So of course I thought it was funny that he used the word demystification, because I wrote a paper called Demystifying Complex Numbers. And so in this paper, I say when complex numbers are modeled using 2 by 2 matrices, then you find that the real component occupies the forward diagonal, or the scalar part of the matrix, and the imaginary component occupies the backward diagonal, or the rotational part of the matrix. And so the forward diagonal is the scalar, and the backward diagonal is the rotar. It's the rotation. And so, and this is what you see, when you look at the Mandelbrot set. This is why there are curves. This is a wave function. This is a hyper wave function, where you're iterating the wave function and getting a higher order function, and iterating it and getting a higher order function. As you zoom into this boundary here, you're getting higher and higher and higher order functions, which is why you see really super high curvature as you get closer to the I'm going to call it black hole, to the black hole. So this is very interesting in terms of the higher order wave functions. And actually Eric Dollard mentioned something in his paper about high order, super complicated wave functions, creating super complicated waves. And so he shows a graphic of some, fairly complicated waves that you might find in electrical systems. And, so he's talking about waves on top of waves on top of waves. And so I found that interesting that, he was talking about that, because that is how I see the Mandelbrot set. So then he goes on to talk about the different types of current, the different types of electrical phenomenon. So he says, in the study of electric phenomenon, attention is usually focused on only 2 forms of electric waves, those of alternating current and continuous, or direct current, which is also continuous. So while these forms are representative of the commercial application of electricity, they only represent special steady state cases. So even AC is considered a steady state condition. So it is known that during switching operations and in the process of modulation, other forms of electric waves appear due to energy readjustment within the system. These waves are known as electric transients. Okay, so we've talked about transients before. Transients are temporary. Transients are impermanent conditions. And so theoretical understanding of these phenomenon is usually quite vague. People don't tend to study the transients because they're more interested in the continuous condition of power delivery, of energy delivery. So these transients give rise to a new pair of waveforms, the oscillating currents and the impulse currents. So thus, in general, the variation of electric quantities with respect to time can be divided into 4 categories. So you have the continuous currents, the DC currents, where nothing changes over time. So the time rate of change over time is 0, so nothing changes except for the current delivery, or the current, the motion of the current in whatever direction it's going. Alternating currents, which do have a time function, a non-zero time function, and that function is in radians per second, so that is an angular frequency. Alternating current is usually expressed in terms of angular frequency. And then you have these two that don't get talked about very much, which are impulse currents, IC, and their time function is in nepers per second. I'm not really sure how to interpret nepers other than the fact that it is a like a power. So this is a unit, kind of like radians is a unit. It's an unspoken unit. This is also an unspoken unit, and this is like a power law or a logarithmic law. And so this is a something that changes sort of the power change over time. And so, and then the oscillating currents is another kind of current. And so here are three examples of what he talked about here. You have the impulse. So this is what he calls an impulse, and this is changing power over time. So it increases quickly and then dissipates, so that it is the changing is nonlinear. It's non-linearly changed, unpredictably changing, maybe even. So you've got your impulse currents and your oscillating currents. So you got continuous DC. Actually, continuous DC would just be a flat line. Any of these lines could be continuous DC. Alternating current, of course, this is continuously alternating. That's why it's still continuous. It is still a continuous function because it is always going to the same peaks all the time, always going to the same valleys at the same, So this is still considered a continuous. So he differentiates between continuous currents and, alternating currents and oscillating currents. Oscillating currents are currents that oscillate like a sine wave, let's say, but their peaks change over time. So it gets, stronger or it gets weaker. It gets stronger and it gets weaker. So and so I think he interprets this as, he would call this production, where it goes from smaller to bigger, and consumption, where it goes from bigger to smaller. Now I'm just interpreting it, like, because I read this paper 10 times, I think that's what he means, that this is different than just pure AC. So it's when something changes, increasing in power and decreasing in power. And so so these are the four really, because of DC. So you got the continuous DC, which is a flat line, alternating current, impulse current, which is this one up here, and oscillating currents, where it is oscillating, but it is also changing in terms of power over time. So then he goes on to talk about the graphical representations of electrical phenomenon and mathematical representations, and he's sort of comparing them to, pro and contrasting different methods of representing electrical phenomenon. And this is the point really of this paper. The point of this paper was Eric Dollard was trying to come up with a mathematical representation of electrical phenomenon that would be easier to understand and easier to implement. I think that's the important thing. Easier for for practical applications. And so, if you understand, if you can, write down the formula and you understand what they mean, and you can get the answer very quickly, or write a computer program to do it to give you the answer very quickly and intuitively, that is really what you want. And I think historically the math behind the theoretical, at least electrical phenomenon, has been a little obscure, a little obtuse. And so hopefully, what I want to do here is I want to try and clear it up. And although Eric Dollard took a great step to improve the language, I think we can improve it much more using the 2x2 representation of complex numbers. So then he goes on to talk about the graphical representations of electronic phenomenon. This is how we graph things to be able to do calculations and to calculate what we need for electrical circuits, etc. And so, so here he says the primary drawback of the graphical and trigonometric methods is that they serve as misrepresentations of the electrical waves under investigation. So what he's saying is they don't really tell you anything about the wave phenomenon that's going on under the hood. This is just a convenient tool for getting the right answer. So you plug these into the equation, you get the answer you want, but they don't serve, so these representations are actually misrepresentations. Sorry, these representations are representations of two-dimensional space that is a plane or a surface. So this is representing a plane or a surface, but not the real electrical phenomenon. Okay, so so in this situation here, yeah, we've got the resistance on the real axis. Okay, this is the real and the imaginary axis. You've got the, so resistance is on the real axis, and the reactance, this is the inductive reactance actually, is on the positive y. So this is positive real resistance, and positive imaginary is reactance. And so this is how they draw it on a graph. Okay, this is how they draw it on a graph, and they square each component, take the square root, and they get something called impedance, and that they use that to, you know, build their electrical circuits. But this is just a graphical representation. It doesn't represent physical reality, and I guess what Eric Dollard is trying to get to is a representation that is closer to representing the wave phenomenon, the physical reality of what's going on. But in modified complex numbers, this is how I represent this graphic. Okay, so using modified complex numbers, using the complex number notation, the 2x2 matrix notation of complex numbers, I can represent the real component and the imaginary component in a 2x2 matrix. And so here you see I'm calculating the impedance. The real component goes on the forward diagonal and has the same sense. So this is how the complex numbers work. If you watch my video, Demystifying Complex Numbers, you'll find that, or if you read the paper, then you will know that I represent real numbers as on a 2x2 matrix, and the real numbers always have the same sense. They're either both positive or they're both negative. In this case, resistance, they're both positive, and in the reactance, the upper right corner is positive. This is the positive imaginary number. This is I times the reactance, and so we've got the reactance on the backward diagonal of the complex number. And when you add these two together, now in this paper, Eric Dollard says something like, when you add, you know, the real and imaginary components, you're not really adding them, you're just combining them, or something like that. That's what's going on. So you don't add them in the traditional sense. When you add a real number to an imaginary number, you are combining them. So basically you can put them into the same matrix. And so this is the impedance, the full impedance. This is the everything you need to describe the impedance of the electrical system is in this matrix here. And so as I got this from Robert Distinti, the notation that he uses is when you put square brackets around a value, it means it is a 2x2 matrix. And so the impedance is with the resistance on the forward diagonal, the reactance on the backward diagonal, and when you add them, you're really just combining them into one matrix. And so this is the trick to simplifying, I think, electrical phenomenon, the description of electrical phenomenon, because, you know, everyone knows, especially a computer scientist knows, that the forward diagonal of a 2x2 matrix is a scalar, and the backward diagonal is responsible for rotations. And so when we're talking about rotations, we're talking about these angles here. Okay, we're talking about rotating from real to the imaginary to the real to the imaginary to the real. And he's got some graphs in his paper that show that. So this is what we're talking about when we talk about rotations. We're talking about rotations in between the real and the imaginary components. Okay, so let's just have a look at this one more time. Forward diagonal is a scalar. Backward diagonal is a rotar. It is the temporal component. This is atemporal. This is temporal. These are incommensurate principles. Okay, so I think I might have mentioned that in my one of my videos, maybe the Demystifying Complex Numbers video, where I describe the forward diagonal and the backward diagonal as incommensurate principles. Okay, so the forward diagonal is responsible for something. The backward diagonal is responsible for something completely different. And so different elements of the electrical system, different parameters of the electrical system, some belong on the forward diagonal and some belong on the backward diagonal. Oh dear, I have to plug my computer in just a second. Okay, so where was I? Oh yes, the forward diagonal has a purpose. It's a scalar. The backward diagonal has a purpose. It is responsible for rotations. In computer graphics, it's responsible for rotations. And this is the true, complete description of the impedance of an electrical system that has a resistor and an inductor. So this, of course, is only the impedance for the inductive reactance, or what Eric Dollard calls the magnetic inductive reactance. So what about capacitive reactance? Well, recently I asked you to watch a video. I posted it on my community section. And so here is the difference. I redrew this image here. I redrew this graph here. I reproduced it here so that I can show you the difference between inductive reactance and capacitive reactance. So here on this graph and on the previous graph, the real component is on the horizontal axis. This is positive real, negative real is over here. This is the imaginary axis. Positive imaginary is up. Negative imaginary is down in both of these graphs. And so here is the inductive reactance from the previous slide. And so I redrew it here to show make it more clear that this is the real axis and this is the imaginary axis. And so as you can see, for the inductive reactance, this line here is in the positive real, positive imaginary quadrant. Okay, so this is going to be a positive real, a positive imaginary distance or point right here. And so for the inductive reactance, the impedance is in the positive real, positive imaginary direction. But in the case of the capacitive reactance, it appears in the positive real, negative imaginary quadrant. Okay, so this is positive imaginary up here, this is negative imaginary down here. So basically what we're doing is we're flipping about the real axis. And so now we are in the negative, territory of the negative imaginary numbers. And so how you deal with this, so here is the modified complex version of the inductive, the impedance in the inductive reactance case, where you have a resistor and an inductor. And you can see that you've got a positive in the upper corner and the negative in the lower corner here. And so for the case of the capacitive reactance, when you have a resistor And a capacitor, you have capacitive reactance. What happens is the capacitive reactance is on the backward diagonal, but the sense is flipped. So you've got the negative value in the upper right hand corner and the positive value in the lower left hand corner. And so this is because the capacitive reactance is in the negative imaginary numbers. So the negative imaginary, let me just go back to my identities here. The negative imaginary identity has the negative in the upper right hand corner and the positive in the lower left corner. As you can see, that's the negative I, or in Eric Dollard's case, it's negative J. So negative J is negative I, negative imaginary. And so you can see, let's go back to this slide here. So you can see the difference between the impedance calculated in an inductive system, where there's an inductor and a resistor, and this is the impedance calculated in the capacitive system, where you have a capacitor and a resistor. And so if you have both a capacitor and an inductor and a resistor in the system, then you've got all the cases. You have to add them all together. So what I would do if I were doing this using modified complex numbers is I would put the resistor is on the forward diagonal, so I put it in its own matrix, and I put the inductive reactance in its own matrix, and I put the capacitive reactance in its own matrix, and then you just add them all together. So when you add matrices together, you add the, let's say, the upper left corner together, so you get R resistance plus 0 plus 0, so that's R. And then let's say we're doing this component here, so you've got 0 plus the inductive reactance minus the capacitive reactance, so you have the XL minus XC in the upper right hand corner here, and in the lower left corner you add 0 minus XL plus XC, so now you've got plus XC minus XL in the lower left corner, and then you add the R plus 0 and you get the resistance here. So the resistance is on the forward diagonal. The combination of the reactance is on the backward diagonal, and you can see that you have XL minus XC and XC minus XL. These are complex conjugates of each other. So the inductive reactance is the complex conjugate of the capacitive reactance, and or the capacitive reactance is the complex conjugate of the inductive reactance. And so this is basically what I was able to extract from Eric Dollard's paper. There's a lot more. There's a lot more that I may or may not get into, but this is really where I wanted to get was how to rewrite Eric Dollard's language in terms of modified complex numbers. And so the paper is quite complicated, and I debated whether to review the whole paper, and I really felt that if I reviewed the whole paper, it may confuse you more. So I may get into this deeper. I'm going to think about it, but I really want to get this snapshot out there to show you how to use modified complex numbers to solve a real problem in a real circuit where you have resistors and inductors and capacitors, and how to compose the complex matrix when you have a resistor, a capacitor, and an inductor. So hopefully this is a little bit more clear. I hope that this makes sense. There is a lot more to say on this, and I will get into this in more detail. But for the sake of this video, I think this is enough. This is enough for you to take in at one time. So I will try to get into this further. There's a lot more slides that I've actually made, but I don't want to get into this right now. I will for sure get into this at a future date. So hope you're having a good day, and well, I'll be back.